All right, so in the diagram, the circle is inscribed in an equilateral triangle, and we want to find the area of the shaded region. So as far as the strategy goes, the area should be triangle minus the circle. Okay, the triangle is not too bad. We've dealt with equilateral triangles before and finding their area, but the circle is what is going to make this problem pretty challenging. When we get to special right triangles, when we get to the Pythagorean Theorem and right triangles in general, we'll certainly learn many ways to simplify this problem. However, we just don't have that math knowledge yet, so we'll just have to do the best with what we've got so far. So obviously there's not enough room here, so just recopy that diagram down below. And again, we want to find the area of the shaded region. And we said that in order to do that, this area should be the triangle minus the circle. So let's concentrate on the triangle part of this first. The equilateral triangle, anytime that I want to find an area, I need a base times a height, so that was going to be my height there. On an equilateral triangle, whenever you draw in the height, you always cut this base in half down here. So this, the right side of this right triangle here, this should be 7 centimeters. Okay, so now I want to use, let's color this nice and pretty. I'm going to use the Pythagorean Theorem on this right triangle over here. I said color it in nice and pretty, and so it looks like a preschooler just colored that in. That's just how I do it. Okay, so Pythagorean Theorem, to get this height, we'd have h squared is, whoa, hey, that's not right, plus 7 squared is equal to 14 squared. H squared plus 49 is equal to, I think that's 289. No, 196. Of course it's 196. What am I thinking? All right, and then subtract my 49 from the other side, and I get 147. H squared is equal to 147. And then take the square root. H is equal to the square root of 147, which is okay, but I want to put this in simplest radical form. I want to simplify that square root. So I want to think of something that's going to go into this 147. Now, it ends in a 7, so that's going to be tricky. Maybe a 7 goes into it. Maybe something like a 3 goes into it. So as far as the 3 goes, if I look at my digits, 1 plus 4 is 5, 5 plus 7 is 12. The sum of the digits is 12. That's a hint that 3 definitely goes into this thing. So 3 into 14 goes 4 times with 2 left over. And then 3 goes into 2749. And then we just found ourselves a perfect square, 7 times 7. So we've got a pair of 7s. One of those gets to come out. And then the 3, oh, poor 3, doesn't have a friend, has to stay at home inside the square root. So we've got ourselves our height. So 7 square root of 3. For the area of the triangle then, the equilateral triangle, 1/2 the base length, the whole entire base is still 14, times my height, which we just discovered was 7 square root of 3. Okay, and I can do some canceling out here. This 2 and this 14 to leave a 7 behind. And now whenever I multiply this 7, this red 7, by the 7 square root of 3, remember that you're treating your square root of 3 like it's a variable, like it's an x. So as if this is a 7x. If I multiply 7 times 7x, I would get 49x. Likewise, the area of this triangle should be 49 square root of 3 centimeters squared. All right, so there's the first part of this problem. Now the second part is going to involve me trying to find the radius of this circle. All right, let me import this picture in here again. Shrink it down. Okay, there we go. All right, so let's say I draw in my radius. And that's what I need to try to find. Sure, it's part of this whole entire height that we had in there before. Let me draw that thing in here. And then maybe just highlight the section of this. That's the radius. Okay. It looks like there might be some sort of special relationship. Like, it looks like this is definitely not half of that whole thing. It looks like it might be, let's say, 1/3. And that is a relationship that we will learn in another lesson. It is not something that you would just know. It's not necessarily something that would be obvious to everybody who is working this problem. So we're not going to use that knowledge. We're going to instead draw in another right triangle here, this one to this vertex down below. And we're going to create another right triangle we can hopefully solve by the Pythagorean theorem right here. Okay. All right, but I got to label some parts on it. So we discovered from the previous part of this problem on the right triangle that the height here is 7 square root of 3. We know that this base down here is 7. And the blue segment, the blue vertical segment part of the height, that's our r. I don't know exactly how big that is, but I'm going to try to figure it out. Now, as far as the hypotenuse goes on that one, you don't know what that one is either. So it's not like you can use the Pythagorean theorem on this green right triangle in order to figure out what r is. So we've got to do it another way. So the two right triangles that are in the picture currently, the one that we used up here to solve for the height, and the green one that I just drew in, these things are similar. These are similar triangles. And similar triangles means two things. It means their angles are congruent, and it also means that their sides are proportional. Proportional means that we're just going to set ourselves up a proportion, equal ratios, and cross multiply in order to find our radius here. So I'm just going to quickly redraw each one of my triangles, but I'm going to face them in the same direction so it's easier to see what the relationship is between each one of them. So this one's going to be the larger right triangle. Larger right triangle, the one that has the height in it, which was the 7 square root of 3. And down here at the bottom, that's my 7, and my hypotenuse here is 14, the side of the equilateral triangle. Now I'm going to draw the green right triangle, but I'm going to flip it around so it's oriented exactly the same way as the larger one that I just drew. Here we go. And now let's match up each of our pieces. The 7 that's down here in the bottom, this 7 is on the longer leg, which, whenever I rotate this thing around, is the vertical segment. So this one is 7. Okay, and now if I look at my r, which is, the whole point of this whole thing, what I'm trying to find, it's on the shorter leg, which is down on the bottom down here. So let's put an r there. I don't need the hypotenuse because you just need two parts that match up in order to set up your proportion. So the two parts that match up are this r, and this 7 matches up. So I'm going to write that as a ratio. It's r over 7. That should be equal to this 7, the vertical 7, and this 7 square root of 3 in the same order. Notice I went r to 7. That's the small one to the big one, so I got to keep it in the same order. 7 over 7 square root of 3. And then I can notice that, hey, these two 7s on the right-hand side here cancel out. Maybe I rewrite my proportion then as r over 7 is equal to 1 over the square root of 3. And I solve a proportion by cross multiplying. I'm going to set my cross products equal to each other. These two cross products should be equal. So I get the square root of 3 times r should be equal to 7. To solve for my r, I'm going to divide both sides by the square root of 3. So my radius should be equal to 7 over the square root of 3. And I could leave it like that, but another thing that we don't like besides fractions inside fractions is square roots in the denominator. So I want to get rid of that. In order to get rid of it, I'm going to use a technique that's called rationalizing the denominator. I can multiply this number, or any number, by 1 and not change it. So we're going to multiply this thing by what I call a fancy 1. And that fancy 1 is going to be the square root of 3 over the square root of 3. Because the square root of 3 divided by the square root of 3 is just 1. I'm not going to change its value. I'm just going to change the way it looks. The reason why I chose square root of 3 is because that's the denominator on this fraction here. So whenever I multiply, it's going to get rid of the square root on the bottom because the square root of 3 times the square root of 3 is just 3. So up top I have 7 square root of 3, and on the bottom I get 3. So here is my radius for my circle. So if I go back up here to the picture, remember what we said is that it looked like that blue segment was 1/3 of the length of the whole red one. And we just figured out that this was 7 square root of 3 over 3, which is in fact 1/3 of that length. Okay, like I mentioned at the beginning of this, in the future, after some lessons on special right triangles, after some lessons on some special segments of triangles, any kind of triangles, the centroid in particular, we'll be able to figure out this problem without all of this work. Okay, so we finally found the length of our radius. We should be able to find the area of our circle. It's pi times my radius, which was 7 square root of 3 over 3 squared. I got to square both of these pieces inside here. Since this is all multiplication inside the parentheses, each thing gets squared. I've got pi times 7 squared is 49. The square root of 3 squared is 3. And then the 3 on the bottom squared is 9. And I can cancel out some common factors like this 3 and this 9, leaving a 3 down here on the bottom. And then our final answer for our area is, I got 49 divided by 3. I'm going to leave that up front. 49 over 3 pi. And then the units are centimeters squared. Okay. So going back up here to our strategy, remember what we said is that the area of the triangle is, or the area of the shaded region is triangle minus the circle. So the area, let's change back to black. The area of the shaded region should be equal to our triangle, which we found was 49 over this 49 times the square root of 3 minus, and the area of the circle we just found out was 49 over 3 pi. And then throw our units on here as centimeters squared. You could get an approximate answer for that by plugging it into the calculator, but I'm going to leave this in exact form, just like that.